Hi, this is Asa Musa, and today we will be talking about amorphous metals. These are two commonly used words in the material science industry. We will start off by introducing the topics we will be speaking about in our presentation today. We will start off by talking about the chemical composition of amorphous metals. Then we would go off and talk about the methods of production of amorphous metals. After that, we will talk about the benefits and advantages of amorphous metals over other metals. Finally, we will be talking about the everyday uses of amorphous metals. Now, you might wonder, what is an amorphous metal after all? Well, an amorphous metal, also known as a metallic glass or glassy metal, is a solid metallic material, usually an alloy, with disordered atomic scale structure. Most metals are crystalline in their solid state, which means they have highly ordered arrangements of atoms. Amorphous metals are non-crystalline and have a glass-like structure, but unlike common glasses, such as window glass, which are typically electrical insulators, amorphous metals have good electrical conductivity. Amorphous metals are made from alloys whose constituents may include iron, nickel, and cobalt, and a metalloid or glass former such as silicon, boron, or carbon. Amorphous metals are very strong and reliable. Many times, products made out of amorphous metals include titanium and zirconium. Titanium is highly resistant to chloride-containing media, practically all salt solutions, seawater, a range of acids, organic and inorganic chemicals and gases. Zirconium is highly resistant to a wide range of acids and bases, both organic and inorganic, which makes it an interesting exceptional long-life alternative to other materials in highly demanding applications. These two elements make amorphous metals even stronger and more reliable. The production of amorphous metals is very complex, and there are four main methods for production. We will speak about every one of these methods. The first method of production is the extremely rapid cooling method. This is a metal forming technique used for forming metals with a particular crystal structure by means of extremely rapid quenching or cooling. A typical technique for splat quenching involves casting molten metal by pouring it between two massive, cooled copper rollers that are constantly chilled by the circulation of water. The second technique is the physical vapor deposition. This describes a variety of vacuum deposition methods which can be used to produce thin films and coatings. Physical vapor deposition is characterized by a process in which the material goes from a condensed phase to a vapor phase, and then back to a thin film condensed phase. The most common PVD processes are spitching and evaporation. As we can see here, this picture illustrates a simple optical representation of the method, containing a vacuum, a substrate, the vapor, and the source. The third method of production is the solid-state reaction technique. This is a chemical reaction system in the absence of a solvent. This is driven by four main factors, which are: the first one is economics. This is where we would save money we would usually spend on solvents. The second one is the ease of purification. Since there is no solvent, that means there is no solvent removal post-synthesis. The third one is its high reaction rate. This is due to the high concentration of reactants. And the last one, which is probably the most important one, that it is environmental friendly. The final production method is the ion irradiation technique. This is a low temperature process by which ions of one element are accelerated into a solid target, thereby changing the physical, chemical, or electrical properties of the target. Ion implantation is also used in the fabrication of semiconductor devices and in metal finishing. Now we will be moving on to the benefits and advantages of amorphous metals over other metals. Some of the mechanical benefits of amorphous metals are: 1. Yielding high strength combined with excellent ductility. Their strength can reach up to 2 times higher than that of steel. 2. Their high fracture toughness. 3. High hardness, good wear, and abrasion resistance. This is also shown in ceramics. And 4. Amorphous metals also have isotropic behavior. Amorphous metals also have electrical and magnetical benefits, like high magnetic permeability, electrical resistivity, and being easy to magnetize and demagnetize. Due to those properties, amorphous metals can be perfectly used in applications such as e-motors. And finally, perhaps the most important benefits are the medical and chemical advantages and characteristics. Two of them are high corrosion resistance due to the lack of grain and phase boundaries, and the second being biocompatibility of some alloys. This is used in one of the examples we will mention about the use of amorphous metals in artificial limbs. One cool fact about amorphous metals is a phenomenon called the trampoline effect. This is where a material is made of amorphous metals and inhibits the spring effect. Let us watch this video and then we can talk about it. As you can see, the ball inhibited the spring effect in the bulk material glass container. Because of the varying sizes of these atoms and their random arrangements in the solid, there are no groups of atoms that can easily move past one another. A consequence of this low atomic mobility is a low internal friction that minimizes the conversion of the dropped ball's kinetic energy to heat. Metallic glasses in general tend to be much harder than bulk crystalline metals. Hardness is a measure of resistance to plastic deformation. Amorphous metals are harder because they lack the crystalline defects like grain boundaries and dislocations present in most metals. Now we will be talking about the uses of amorphous metals. Amorphous metals are used widely in the aerospace industry. The high strength of the material makes it possible to modify the design of components and make them thinner and smaller than is possible with standard materials, which is perfect for space shuttles. A further advantage is the low density of amorphous metals, which is below that of steel. This reduces weight, one of the biggest challenges for innovations in e-mobility and aerospace. In addition to their low weight, amorphous metals offer another decisive advantage for the aerospace industry. Unlike other metals, they do not become brittle at extremely low temperatures, and therefore are practically suitable for extreme environments. Thanks to their high creep resistance, amorphous metals can also be used to produce light, small and stable rotor elements, for example for drones. Also, NASA is currently using amorphous metals as a dry lubricant for the Mars rover. This enables lighter and smoother movements. Amorphous metals are also used in the oil and gas industry. Heavy industry also uses various amorphous metals as protective coatings for industrial machinery, on petroleum drill pipes, and for boiler tubes in electrical plants. Also, amorphous metals are used in golf clubs. They improve the performance of players so much that in 2003 the World Golf Association banned clubs containing more than 27% metallic glass related materials in them. And finally, one of the most important uses of amorphous metals is the coating it provides for artificial limbs. The absence of grain boundaries leads to better resistance to wear and corrosion. This helps the artificial limbs be more reliable and last more time with less defects. This can be proven with athletes using them. They apply pressure on them continuously, but they never break. Thank you. This is all I have today about amorphous metals. Thank you for listening.